Do you actually have the link to it? Can you share a link here?
Just a moment, please.
Oh boy, I might try.
Go ahead, Mehmet.
Thank you, Dina. Good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. This evening, we are delighted to have Professor Dr. Maria Kazachenko as our guest speaker. Professor Kazachenko is an assistant professor at the Astrophysics and Planetary Science Department at the University of Colorado, Boulder, and the National Solar Observatory. Before that, she spent 7 years at the Space Sciences Lab at UC Berkeley, California, first as a postdoctoral fellow and then as a research scientist. She is still remembered in lovely Bozeman, Montana, where she did her PhD with Richard Canfield, Dana Longcope, and Yang Qi, and at St. Petersburg State University, Russia, where she received her master's degree in math and astrophysics. Dr. Kazachenko's research group interests range from the storage of magnetic energy in solar active regions to the release of that energy in solar flares, with an emphasis on comparison and integration of observations and simulation. Understanding how this energy is stored and released is necessary to predict solar eruptions and hence the space weather. She was also involved in the development of the critical science plan for the Daniel K. Inouye Solar Telescope, the largest 4-meter solar telescope in the world, with first observations in 2022, last year. Dr. Kazachenko has been honored by the NASA Early Career Fellowship, the NSF Career Award, and the Robert Bartnick Fellowship. Maria, please proceed with your presentation.
Okay, thank you very much for such a generous presentation, Mehmet. And thank you for the invitation to be here. So I'm here to talk about the sun because National Solar Observatory is here in the Boulder, right nearby. And that's why I moved here. And that's basically what I study. And this image that I've chose to show you is supposed to say how exciting the sun is, although it seems very boring. And that's how we think about the sun. Black holes are cool, the sun is boring. But my goal is to show you that that's not true at all. And I'm going to try to convince you and tell you all about that. So here is a typical view on the sun. So let's step back first and start from the basis. That's how we are usually thinking of the sun: sunsets, sunrises. The sun is just shining, everything is boring. Okay, here is a slightly atypical view of the sun during the solar eclipse. You see the moon slowly covering the surface of the sun. And then all of a sudden, wow, you have a total phase, which is truly amazing. And during this total phase, you suddenly see all this immense and incredible structure around the sun that you don't typically see, the solar corona. And then again, the boring phase, the partial phase, doesn't even count as an eclipse. If you haven't seen an eclipse, go see it. Here are some pictures from Great American Eclipse in 2017. So that's how the eclipse looks with the naked eye. You start seeing all this beautiful corona, and then also you see the red color right around the dark disk, which is the chromosphere. Why is it called chromosphere? Because it has the red color. And then the birds stop singing. You suddenly see mountains that you haven't seen before because the transparency of the atmosphere changes around you. It's truly incredible. And then during the partial eclipse, you still see lots of light. So that's why I say it doesn't count at all, because you don't see corona, just slightly different. So go see the eclipse. That's one of the messages of my talks today. So during the total solar eclipse, you suddenly see this solar corona. And there is this incredible structure spanning from the sun all the way outside. So there is this enormous complexity. That's one thing. And then the second thing is the question, what happens with all this enormous complexity as this whole structure propagates outwards towards us? And how do we try to figure out what's going on there? Well, I will try to answer the question, how do we study the sun and how do we know everything we know about the sun? Because the only thing we have is pretty much emission, that's it. But this emission is not very simple. As we know, emission contains different wavelengths, and different wavelengths correspond to different temperatures. So by looking at different wavelengths, you basically look at different layers of the sun that contain plasma with different temperature. And that's how we study the sun. Here's an example sun, as we see in the broadband filter. If you just put on glasses during a solar eclipse, for example, or just if you go outside during the day, look at the sun, you might see if there are large sunspots, these dark spots, which are sunspots. So that's the broadband filter. However, if you start looking into spectral lines, then it turns out that the sun has lots of structure. Here's an example of sun seen in the 1700s angstroms as observed by the Solar Dynamics Observatory flying out there, a mission by NASA. And at this wavelength, you could see the photosphere, the solar surface at 4,500 Kelvin. So pretty hot, but quite cool compared to corona. Then let's look at a different wavelengths. Here is 1600, and you look at hotter lines and you start seeing a higher up above the solar surface, the chromosphere. That's the red part that we've seen during the eclipse. Then a little bit hotter in 304, you see higher up in the corona, 171 angstrom, different filter. You all of a sudden see 600,000 kelvins, and this is corona. And then finally, you could go even higher, but I decided to stop here. Finally, at 193 angstrom, you see 1 million Kelvin. So different wavelengths, you see different temperatures and very different structures. If you just flicker back and forth, you see looking very different. So our sun has this enormous structure in different wavelengths. And here I'm supposed to show a movie. Okay, and here is the movie from Solar Dynamics Observatory. And what you see here is the sun in one day observed in all these different filters. The solar surface is at 1,000 Kelvin, thousands Kelvin, then solar corona is at millions Kelvin. And it's just amazing how exciting the sun looks in all these different wavelengths. So let's go back to the solar surface, to the boring pictures and the visible light, and try to understand what's the force that defines all this incredible structure. Well, I'll tell you the answer. It's the magnetic field. And here is the picture from the same telescope, Solar Dynamics Observatory, of the magnetic field in the solar photosphere, the solar surface. So white color shows magnetic field directed towards us, and then the black color shows magnetic field directed away from us. So you have these bipoles of magnetic fields. Here's one, here's another, which corresponds to this dark spots, the sunspots. So you have this enhancements of magnetic fields located right where the sunspots are. And if you look at the corona, you see that there is the structure that's created by these magnetic fields. And here, these lines, they show actual orientation of the magnetic fields. And you could think of each sunspot as a huge magnet, or the huge magnet located on the surface of the sun that creates all this amazing structure, okay? And I'm just going to flicker back and forth. You see there is sunspot here, and then there is darkening here, which corresponds to coronal hole. That's a place where plasma actually escapes and runs towards us. And then another sunspot. And then there is a filament here, the stuff, the cool stuff that is hanging above in the solar atmosphere, supported by these magnetic fields that don't allow it to fall down. So there is this immense structure, all created by these huge fridge magnets. So again, notice all the similarities between all these different wavelengths, and it's all magnetic fields that creates this beautiful structure. And because the plasma there, the stuff there is so hot and magnetic field is strong, basically all the motion of stuff, of particles, of plasma happens along the magnetic fields, okay? So it's the magnetic field that creates all this structure. So what happens with all this plasma once it's ejected, or once there is some dynamics going on? Well, it actually goes towards us. And a French scientist, during the eclipse, we could observe this faint corona, but also a French scientist, Leo, he actually was the one who invented a coronagraph, which basically blocks this bright core, the bright sun, and then you could see this beautiful corona around, and you could see this immense amount of dynamics. And if any of you have seen beautiful Aurora 2003, these were the beautiful events, so-called Halloween flares, that the sun ejected right in October 31st. That's why it's called Halloween. So all this plasma gets ejected towards us, and then once it reaches, it flows towards us as a solar wind, as a supersonic solar wind, okay? And here is the video from STEREO, Solar Terrestrial Relation Observatory, which shows how much structure there is once this plasma leaves the sun, okay? So the science that studies all these processes happening on the sun is called heliophysics. And here is just a simplified view of what we think the sun is doing. You have nuclear reactions happening in the middle. Then the energy from these reactions slowly propagates outwards. It takes many, many years for this energy to propagate outwards. Then this energy gets mixed in the conductive layer above in here. And then finally, this energy reaches the visible surface, which we call the photosphere, from photons, the visible parts. And then it's in the photosphere where we see these beautiful sunspots, beautiful coronal loops. Sometimes you even have some eruptions. Like here we see a coronal mass ejection, and then it all flows towards us. And here is just a simplified view of what we think is happening during the eruption. We have magnetic fields that reconnect, they change their structure. And because there is so much energy contained in these magnetic fields, we have this huge release of energy. So all the energy actually is coming from the energy of magnetic fields and when they reconnect. And then if we're lucky or unlucky, then some of this energy leaves the solar surface and starts propagating towards us. And here are some beautiful movies from Solar Dynamics Observatory of some eruptions. Here, this one is just a model. And here is another beautiful observation of solar eruption. Here is a sunspot. Then the eruption happens. Some of the stuff cannot get through and then falls back, and some of it erupts and gets outside. So as I said, most of solar activity originates from sunspots. And sometimes there are many sunspots, sometimes there are few sunspots. It's all guided by the solar cycle, 11-year solar cycle shown in here. Where are we now? Actually, we're not even here. So we're somewhere here. Now we're in solar maximum. And the previous solar maximum was 11 years ago. So around 2012, 2013. And then 6 years pass and it's solar minimum around 2018. And then another 5.5 years and you have another maximum. And here is just demonstration of number of sunspots as a function of time. So you have 2010 solar minimum, few sunspots, few flares. Then solar maximum, 2017, lots of sunspot, lots of flares, and then again. So you got the idea. And then another manifestation of solar activity is a butterfly diagram. Sunspots start first appearing at the higher latitudes. So this is the equator. There's one pole, that's another pole. Some sunspot, they start appearing higher latitudes, and then slowly with time, sunspots start being closer and closer to the equator. Okay. So what happens once this eruption happens, and once the plasma escapes from the sun, then this plasma bubble called coronal mass ejection, containing magnetic fields, propagates, and sometimes it passes some planets. And then let's see what happens. If the planet doesn't have the magnetic fields, then all these energetic particles that are quite radioactive, they pass past the planets. And that's what happens, for example, when this disturbance passes Mercury, where the magnetic field is very weak. Okay, so here is Mercury. So no protection, no aliens living there. And then the magnetic fields, the plasma bubble basically continues propagating and goes past the next planets. We also doesn't have magnetic fields. Then this plasma bubble reaches the Earth. Okay, and what happens there? If we didn't have the magnetic fields, then our life would have been very miserable, because all these particles that are contained in this plasma bubble are in the coronal mass ejections are very harmful, very energetic. But luckily we have the magnetic field, yay! So we are safe, okay? We're safe, we're protected. And the only thing, unpleasant thing you see are these beautiful auroras close to the magnetic poles that occur due to magnetic field interacting, the magnetic fields of the coronal mass ejection with the magnetic fields of the Earth. So you have some reconnection, then energetic particles, reconnection, basically the change in the magnetic field structure of the Earth magnetosphere. Then some particles propagate along the magnetic fields lines of the Earth. And some of these particles get ionized. They ionize the molecules in the Earth atmosphere, and then you see these beautiful auroras in higher latitudes. And again, the more energetic this event, the lower is the latitude where you could see these beautiful auroras. That's why we have to go to Alaska to see them. And only if there are very strong events, like for example, Carrington event was one of the largest eruptions seen in the end of the 19th century. You could actually see auroras all the way to Cuba, or you could read a book here in the Rocky Mountains. Okay, so, but how do we understand all these beautiful events, all these flares and eruptions? Well, the problem is that it's hard to understand something when it's so far away and you only have remote observations. Plasma is incredibly complex, it's transparent, it's multi-temperature. There is no way to fully understand it. So for that, we actually use models where we use observations of magnetic fields on the solar surface and some complex mathematical models to try to understand what's going on. And here I will show you one example of such a model that has been generated by me and collaborators. We are actually looking at synthetic loops from a model, synthetic active region, synthetic sunspots. And you will see an emergence, basically a birth of the sunspot on the surface of the sun, shown in, the sunspot is shown basically in blue and green colors. So it's a bipole, and there is another blue and green color. So you would have a birth of the sunspot. And then as the sunspot is growing, as it's developing, we'll see the coronal loops shown in red, synthetic emission, that shows what's going on with the sunspot as it evolves. And here is the top view and the side view. So here is this movie showing, it's based on the real observations of the magnetic fields, but all the emission is fake. It's basically based on the computer model. Highly complex computer model, but nevertheless just a computer model based on physics. And you see that there is lots of activity here, looking kind of similar to what we've seen from the observations of Solar Dynamics Observatory, okay? So what's the idea of all these models? Well, the idea is the following. It's all the magnetic field that defines when will the next eruption happen. So it's all the magnetic field. The problem is that we only can observe the magnetic field on the surface, but not in the volume where it matters most. To be able to predict solar activity and the space weather, we need to know what's the three-dimensional structure of solar magnetic fields. The problem is that we cannot observe it directly. So we have to use models like that to try to understand what's really going on in this volume. And that's the whole purpose of these types of model, to reconstruct something that looks like what's happening on the sun, to really try to understand the physics that's guiding everything that's going on here. So we've seen some eruptions, but the message that I want you to remember after this talk is that sun is not just about eruptions. Sun is very active, even during quiet days. So here we see evolution of the sun as it rotates. Yeah, the sun is rotating differentially. The equator rotates faster. And there are no dynamics and lots of changes going on. So even when we look outside and it looks boring, there are so many things going on that we have no idea about. And this quiet sun creates this immense amount of structure. And here in the center is the sun that's blocked because we want to see the faint area around the sun. And you see that there is incredible amount of structure. There is this constant outflow of the wind, what we call the solar wind outside, from inside out. And the solar winds actually is affect a lot the Earth magnetosphere, even when there are no eruptions. So here we see the Earth, and here is the magnetic field of the Earth. And what the solar wind does, it basically causes this oscillations in the Earth magnetosphere that you observe here. So the color is the density, this is the magnetic field of the Earth. So you have this constant beating caused by the solar winds. So thanks God we have all this magnetosphere that protects us from the harmful solar winds. And these fluctuations in the Earth magnetic fields, Earth magnetosphere, sometimes very strong, especially when you have eruptions. And here is just an example of 4 calculations of the satellite motion. So you have to take into account the drag that's created by the solar winds. And if you don't take it into account, sometimes you could have accidents like the one showed here, the Fall of Skylab in 1979, where the predicted orbit was here somewhere in the ocean, in the Indian Ocean. But because of these atmospheric drag caused by the solar winds, the Skylab fall down. The controlled fall down was not so much controlled. It fell down somewhere in the middle here in Australia. Luckily, not too many people there. So how do we try to understand this immense amount of structure? As I said, it's semi-transparent. It's very hard to understand really what's going on there. And now I'm going to talk about some examples of missions of some new instrumentation that has been proposed and will be built or has been built soon or recently. Here is one, PUNCH, Polarimeter to unite Corona and the Heliosphere, that is supposed to be launched in 2023. And the PI is here in Boulder. It's been led by Southwest Research Institute. The PI is Craig DeForest. And what PUNCH is going to do, it will consist of 4 small satellites that will basically make pictures of this whole heliospheric environment in a very fancy way. So it is going to use polarized photometry, polarized lights, to understand what's really going on in 3D, okay? And what PUNCH hopes to do is to unify the corona and the heliosphere. So right now we mostly either look at the sun or we look what's happening close to the Earth in situ by measuring directly the plasma properties. But what's really going on in the middle, we have no idea. So Punch is going to unify the sun and the Earth and to fill in this missing parts, okay? Another mission is called NASA Parker Solar Probe that has been launched in 2018. And this is a very interesting and revolutionary mission because it basically has been launched towards the sun to burn inside it. But before it will burn, it will tell us everything about the properties around the sun. So again, very similar idea, unifying this solar studies with what's going on here close to Earth. And it has been named after Eugene Parker, shown here. So Eugene Parker was the one who actually predicted solar wind from just theoretical ideas. And here is Eugene Parker, much later, 50 years later, observing the mission that has been named after him, the Parker Solar Probe in 2018 from Cape Canaveral. Truly amazing event and mission. And here is the launch of the Parker Solar Probe mission to touch the sun. Now this, so truly amazing. They're very exciting. This mission has been highly successful. It has already reached the sun, hasn't burnt yet, but it has already done several turns close to the sun, coming as close as 10 solar radii, okay? So very close. And here just an illustration where we are. So here is Earth orbit has been launched here, and then coming closer and closer, all the way to 10 solar radii, so super close. Truly revolutionary mission. So before it will burn, it will tell us about the solar wind properties, density, temperature, things that we could never predict just using remote observations. So the goal of this Parker Solar Probe is to understand the structure and dynamics of the sun's corona and to connect the sun with what's going on around in the heliosphere, okay? And here is one of the exciting examples from Parker Solar Probe. It has found this so-called switchbacks, that the magnetic field is not laminar at all. It has all this very highly dynamic wiggles. And here is the artist's way of trying to show this wiggles. So you see these wiggles here, but we still haven't figured out. There are a bunch of ideas what's going on, but still no agreement on what's causing these wiggles. Okay. So the surface of the sun, on the other topic, the surface of the sun has this enormous amount of structure. And trying to understand the structure, we use very large mirrors, up to 4 meters, solar telescope. And here is an example of observations from Swedish solar telescope in a nice island, Canary Islands in Spain. And it's a sunspot. So we have a sunspot dark, and then there's granules around it. And here is a picture again from the Swedish solar telescope on Canary Islands. The diameter of this telescope is 1 meter, but we still don't understand what's going on in the sun. And for that, starting 2022, we finally finished building of the DKI solar telescope on Hawaii, Maui, called DKIST, yes, the telescope called DKIST, and it has been built by National Solar Observatory, again, here in Boulder. Well, the observatory is in Hawaii, but the National Solar Observatory is here in Boulder. And the DKIST will resolve structures on the sun as small as 10 kilometers. So that's amazing. So DKIST science objectives are many. Not going to go into details, just going to show you a picture of DKIST. It has 4 meter diameter mirror. It's on the top of Haleakala Mountain on Hawaii. And it has just started observing last year. So we're very excited, and my research group is still waiting for the observations from this telescope, hopefully soon. Here are observations of the center of the sun. So here is the center of the sun, and you actually are looking at the boiling center of the sun. This is the photosphere, seen in a visual spectral line. And we see that there is this constantly boiling surface of the sun, of our main star. So from here, I just want to say that we're no doubts are entering this golden age of solar physics, at least of solar magnetism physics, because we have all this beautiful suite of different instruments. Parker Solar Probe is going to touch the sun and will tell us everything about what's going on closer to the sun in terms of magnetism and particles properties. Another mission that I haven't mentioned, but it's another exciting mission, has been launched also recently, 2020. It will observe the sun from different points, so from different vantage points, and will tell us about, and will also come closer to the sun to tell us about both solar wind properties and also the poles. I'm sure you've seen these beautiful images from Juno instruments of the Jupiter poles, something that we could never have thought about. It's amazing. So hopefully with Solar Orbiter, we'll get a peek of what's going on there. Finally, DKIST, that has just started observing, will look at the sun at the highest resolution ever. And Punch, that I've mentioned, the 4 satellites, is going to connect it all, the solar corona with the heliosphere. And on that note, I want to that if you think the sun is boring, there are no quiet days. Even on the most quiet days, the sun is filled with waves, energy bursts, explosions that launch plasma into the solar system. And we're so lucky to live in this quiet environment in the Earth magnetosphere. Sun still has lots of mysteries, and that's why I'm employed and have a large research group of young souls who try to understand some of these mysteries. But with so many instruments coming on board, we hope to understand at least some of them. And I thank you very much for your attention and for the invitation. And I wanted to give you a homework. So next solar eclipse will be in 2024. If you haven't seen an eclipse, it's a truly spiritual experience and very transforming experience. So if you haven't seen it, make sure to see one. And it's going to come very close to here. Thank you, and feel free to ask any types of questions. There are no simple questions. Thank you very much.
Thank you, Maria.
Thank you, Maria.
Yep. You're welcome. My pleasure.
Let's see. Let me ask my question first. What was your PhD on, Maria?
My PhD was on solar eruptions. So I was trying to understand how these complex magnetic field structures form during the eruptions. There are several competing theories there. Some people say that magnetic fields, they twist. So the whole question that how these magnetic fields that reconnect are formed, they are twisted, but we don't know how. And one theory is that they get twisted very gradually over many days. And then another theory is that during eruption, they somehow become more twisted. So in my PhD, I basically use observations and modeling to try to understand it. So all very related to eruptions.
Did you use both observations and simulation at that time?
Yep. Yep.
Ron is asking, how can amateur astronomers like those of us in DAS help contribute to solar science?
Good question. That's an excellent question. I guess the best way to contribute to solar science is doing outreach, to bring more young souls to this field of research. That's one thing. Because still there is so much that we could do in terms of outreach, especially underrepresented communities. That's one thought.
Ron?
Okay, and then there are lots of people also contributing to solar eclipse observations, trying to observe what's going on there during the eclipses in terms of coronal structure. I'm
Okay.
not sure how, though, very scientifically useful these studies are.
A
Yeah, hard to
comment or comment that goes along with the question I asked. I know that during the 2017 eclipse,
Yes.
amateur radio operators conducted radio propagation studies during, well, before, during, and after totality, and of course found some interesting things. And that was done in conjunction with professional science. So there was some good contributions there from, we'll call it the amateur community, in that case, amateur radio.
So you see, you know far more than I do. Yes, yeah. I'm sure there are studies like that, because sometimes there are also community campaign studies where, for example, during the solar eclipse, I know that there was a campaign when they collected solar eclipse images of people from all over the United States in 2017 to try to understand what's the high cadence coronal dynamics is.
I remember that. That was a
Yes.
good one.
Yeah, that was a good one. I'm not sure what exactly came out of it, but once in a while there are campaigns like that, that's for sure, yes. And there is a lot of outreach being prepared, and I'm sure campaigns like that for the upcoming eclipse. Yeah.
Great. Thank you.
Yeah.
Steve Barr is asking, has it ever been confirmed that the corona is so much hotter than the photosphere as a result of acoustics?
So so the question of what's causing the problem is exactly the confirmation, not the absence of theories. There are so many theories that could potentially explain. The question is how to figure out which one is the correct one. Yeah. So
Mehmet, I don't know if you
that.
saw, but we had some earlier questions.
Okay.
Ed Ladner had the first one. He asked, with the Parker
Mhm.
mission going to hit the sun, are we going to attempt to observe the impact?
It's an excellent question. It's a good question. When will it happen? Let's see. I have no idea. Yeah. Let's see. I'm not sure. I haven't heard of campaigns like that, but yeah, and it doesn't even say when it's going to happen. Yeah, for sure I have to organize something.
Richard Schultz is asking, do you think the solar wind colliding with molecules in the Earth's atmosphere created some of the water the Earth has?
Unfortunately, I don't know how to answer this question. Yes, I don't know. Yeah. Yeah, outside of my expertise.
Any other questions? Did I miss anything, Dina?
No, I think those were the
I have a
first
question.
two.
Who has a question?
I do. I have a question.
Yes,
Hi,
David.
David.
Yeah, first it was more of a comment than a question. Sorry I was late tonight, but I did have a conflict, but I did make it here in time to hear the conclusion of what must have been a wonderful presentation. And as I was listening to you, I was imagining the contributions that NASA has made just to our observation of the night sky, of the planets and the sun. I'm a little surprised that the Parker Solar Probe was so late in the litany of NASA missions sent out, but it's in a way not surprising because getting to the sun is a very difficult thing.
Yeah.
But I want to congratulate you on a wonderful, wonderful presentation. I have a little quotation today, and it is actually related in a way, and it comes from Abraham Payas's biography of Albert Einstein. And when Einstein finally used his theory of general relativity to explain quantitatively the secular rotation of the orbit of Mercury, and that rotation was discovered by Leverrier, same man who discovered Neptune, without the need of any special hypothesis. And he writes, this discovery was, I believe, by far the strongest emotional experience in Einstein's scientific life, perhaps in all his life. Nature had spoken to him. Thank you very much, and a wonderful presentation. I'm glad I got to see part of it.
Thank you so much for your kind words. Yes, Yeah, that's true that for NASA it took 40 years from the first ideas from the first ideas of such a mission till the launch because of all the technical difficulties.
Yes.
Any other questions? You can raise your hand either physically or through the token. I don't see any. Ed is saying what? I have a ballot result. Okay. Well, before
Well,
that,
first, yes.
are there any other questions? I guess we should thank you very much, Maria. I think this was as David said, it was an excellent presentation, very informative, and we very much appreciate your preparing and presenting it. So thank you very much.
Thank you.
Спасибо, Maria.
Не за что. Thank you.
Thank you.
Yeah.
Thank you. And
Unfortunately, I have some home chores, so I'm going to leave here. But thank you, everyone. And if anyone has any questions, feel free to contact me via email.
Thank you. Have a good evening.
Good evening.
До свидания.
До свидания.
Okay. Very good, Ed. Please do go ahead with the election results.
May I share my screen?
Yes.
All right, you should have on your screen the election results. It will surprise no one that Dina, running unopposed, was elected with 98%. Treasurer Chris Hamlin, also running unopposed, won with 99%. And for our executive board, which there were 8 vacancies, we have the following new board who will be coming in. We have Bill Cast, Ron Rannick, Joe Gafford, Jack Eastman, Joe Godwin Austin, Joe Panetta, Toby Sheets, and Catherine Bond. Congratulations to the winners of the election.
Thank you, Ed, and welcome to the new incoming trustees.
If someone wishes to post the link that I provided earlier to the news section on the member portal, I've reposted it. That will be the sticky results for the outcome.
Okay, very good. Very good. Yes. And we have an announcement coming out in an email to all members shortly, correct, Ron?
Yes, sorry, it took me a second to get to the unmute button. Yes,
Okay.
there will be an email announcement being sent to the membership probably this weekend, which will include the election results, some other announcements. There'll be some information about the spring banquet and the upcoming InReach on February 11th.
Wonderful. Okay. Well, Ed, thank you for your service as our election coordinator. We appreciate you doing this job for us.
Thank you. I believe I have completed the election coordinator tasks, but I remain available to provide certification of the election. And if anyone wants to challenge the election, I have an audit.
Okay, very good. That's good to know as well. All right. Well, I'm going to go ahead and stop the recording at